Hi, everybody, and welcome to my talk on automatic machine learning with the human in the loop with Dabble. My name is Andreas Mueller. I'm a scikit-learn co-developer, and I'm a principal engineer at Microsoft, though a lot of this work has been done while I was at Columbia University. I want to start with how I usually approach a machine learning problem. So in machine learning, you usually start with a task definition, and it's quite an essential part to see how you phrase your problem as a machine learning problem. Once you've done that, you start with collecting your data, cleaning your data, doing some exploratory analysis and visualization. Then you start doing model building, offline model evaluation, and finally you do online model evaluation or some evaluation within the logic of your scientific experiment or within your business. However, this is not really a linear workflow. This is more of a feedback loop where you go back to previous steps. I drew this here as a cycle, but really it's more like a fully connected graph where after each step you might decide that you want to go back to one of the previous steps. So say after data cleaning or visualization, you might see there's data quality issues and you might go back to change how you collected your data, or after model building, you might figure out, oh, the model couldn't deal with particular aspects of the data, and so might need to clean it differently, and so on. And what I see many data scientists do is to really focus on the model building part and try out many different models and do a lot of hyperparameter tuning. And we have great tooling to do this, and it's a lot of fun, and so people are really focused on this aspect. But what I want to talk about in this talk is to think more about how to make the whole process smoother, because very often the gains come not from like iterating more on just the model building, but iterating on the whole process and see how the model you build integrates into your business product or your scientific process, and how you can iterate very quickly within this whole feedback loop and not just work on the model building or not just work on visualization. And so to do this, what I really want is I want to make each of these steps fairly simple and very easy to do, so you can iterate quickly and go back easily to previous steps. So right now I find that a lot of these steps are not really easy enough. In particular for the data exploration, visualization, and the model building. So, as you might know, I'm a big fan of scikit-learn. I've been working on it for a while, and I think it's a great library. I also think pandas and seaborn are great libraries, but I feel like if I want to do standard tasks, I still have to do too much work. So here I'm loading standard benchmark data set, the adult data set with pandas. This is a classification data set, and so I might want to look at some of the continuous variables and do some plots. And if I want to do this with seaborn, it takes me only a couple of lines, but these couple of lines are actually quite involved. I need to select the right d-types. I need to do some melting and some reshaping and a hazard grid. And so given that this is a super standard plot, this seems a little bit overly complex to me. And I really would like for this to be sort of my hello world of data visualization, like just plot me the stuff for classification. Similarly, on the same data set, if I want to build a machine learning model with scikit-learn, so a standard model I want to do might be logistic regression model, and obviously I want to tune the hyperparameters of the logistic regression model. And so if I have some missing values, some categorical and continuous features, the way basically the most simple model looks like with scikit-learn, if I want to do hyperparameter tuning, is this here. And again, it's maybe not too bad. So for me, it's relatively easy to write this down, though I've also worked with scikit-learn for a long time. But I think it's just too much work to just get something going. And so if I have to write this much code and this much boilerplate to just get a simple model going, I think that makes it very hard to iterate quickly. On the other hand, you have some automatic machine learning frameworks out there. And I really like particular AutoScikit-learn, which is done by a group in Freiburg, which builds on scikit-learn. And I think these are great tools, but I think the focus of these tools is more to build the very best model given quite a big compute budget. So in the documentation, you can see on this digits data set, which is a very simple data set that's built into scikit-learn. Their simple example runs for about an hour on this very small data set. And if you want to really squeeze out the last bit of performance on your data set, I think this is the right approach. But if you want to just get something going quickly, you don't want to wait for an hour. And if your data set is bigger, you'll probably wait for much longer than an hour. But something like an hour or several hours is a pretty realistic budget for most automatic machine learning tools. And so really, I want to iterate more quickly in this whole workflow. I don't just want to spend a lot of time on the model building process. And so maybe later on, in the once I'm pretty confident about my data collection and my evaluation and how everything fits together, then maybe I want to use some more advanced automatic ML and spend a lot of compute on really getting a good result. But this is not where I usually want to spend the time in the beginning. And so trying to build easy-to-use solution for all of these different pieces, I came up with this new library that I call Dabble, which stands for Data Analysis Baseline Library. So the goal here is to make it really easy to get a good, robust prototype for a machine learning problem so that you can easily and quickly iterate on cleaning the data in a different way, collecting more data, evaluating models, doing model interpretation, and so on. And so basically, I built some tooling and some different functions for each step in this cycle. So the data collection is still up to you, and I assume that you can load your data into pandas data frame. So this is all assuming in memory. And so once you have your data frame, you can call dabl.clean, which does some basic cleaning for machine learning. There's dabl.plot, which does some visualization and exploratory analysis for you. There's dabl.any classifiers, which does some automatic machine learning, but tries to do this very quickly and very efficiently. And then there's dabl.explain, which tries to explain any model that was built. And I'll talk through all of these in a little bit more detail. And then what's maybe the most important part is seeing how does this model fit into your actual use case. And this is where you actually have to think again. And so this is often where I feel like data scientists don't spend enough time seeing how does a particular model fit into our overall process, because they get too hung up into the model building and model evaluation maybe. All right, so let's go through some of the tools that we have in Dabble. So let's start with the data cleaning and preprocessing. So there's basically two ways you can do this in Dabble. There's a clean function that I show here on the Ames housing data set, which is like a relatively standard but a little bit dirty regression data set. It has quite a few columns, as you can see here, 82 columns. They're like categorical, continuous IDs and missing values and so on. So if you want to do some quick and dirty prototyping, you can just do dabl.clean, which will create a new data frame for you. It will tell you how many columns are continuous and categorical, if there's 30 columns that have some strings in them, or maybe some missing value that was encoded as a weird string. And if there's useless columns that are maybe nearly constant, or that look like IDs or like an index or something like this. And so then you get this clean df out, and you can keep working with this data frame. So this detects type, even though you can override some of the type detection, it deals with missing and rare values. It figures out what is ordinal or categorical and which integers should be continuous or not. And it detects a couple of different useless columns. So there's also a preprocessing class. This preprocessing class basically provides a scikit-learn transformer that automatically puts together a column transformer and pipeline that does all the pre-processing. So this really cuts down on the boilerplate you have to do, but it still gives you full control over what kind of model you want to use. So this allows you to very easily create a scikit-learn pipeline without having to worry about the pre-processing. So next, we have some tools for visualization, and these are basically all exposed as a single function, dabl.plot. So here I'm using this adult data set again, and so you just load the data frame, and you give the data frame to this plot function, and you tell it what the target column is. So everything in Dabble, either you can pass it the data as X and Y, where Y is a separate ND array, or pandas series, which is the scikit-learn interface, or if you have everything as a single data frame, you can give it the full data frame and the name of the target column. So we can use either of these two interfaces for all of the functions in Dabble. And so if you call this plot function, it will just do plotting both for categorical and continuous variables and see how many variables there are. There's some selection. So you can see here there's many categorical features which are shown using these mosaic plots. And you can see that if there's very many categories, for example, in this marital status, then some of them that are very infrequent get grouped together in this dabl.other, and only the most common ones are shown. And so if you're familiar with mosaic plots, basically the height of each of the bars tells you how many values are in each of the category, and then the width tells you the balance between the categories. So there's this two-class classification data set showing where blue represents the people that make less than $50,000 a year, and orange represents people that make more than $50,000 a year. As you can see that not only what is the balance between the different categories, but also what is the proportion of these two classes within each category. And so there's also a couple of univariate plots. In particular, there's like these class histograms. So if you have a multi-class data set, you can show all univariate histograms for a particular feature for all the classes in a single matplotlib axis. So this allows you to make much more compact plots. This will also automatically cap at a certain number of plots and will sort them by their statistical significance. So already talked about this mosaic plot. You can also do mosaic plots for multi-class or for more categories. So here, this is a data set where each of the variables is binary, but we have 3 categories, and so you get these stacked plots. So there's 3 classes here, blue, orange, and green. And you can see, for example, for this variable A89, that so you can see that if the class is 0, then you're certain it's not orange. Sorry. If this feature A89 is 0, then it's very likely to be green. It's guaranteed to not be orange. Whereas you have a small likelihood for it to be blue. And if the feature has the value 1, you have about equal proportions among the 3 classes. And you can also see here that the classes 1 and 0 are relatively equal likely. The class 1 is a little bit more common than the class 0. The dabl.plot also shows pairwise plots. If there's more than a certain number of features, it actually will not show all pairwise plots because that would be very overwhelming. Instead, it tries to figure out what are the most interesting pairwise plots. And so this is basically building on top of the idea of economics, where you try to evaluate how interesting is a plot. And here, the particular metric that we're using is that we look at these pairwise scatter plots, and we want to find out how well can a very shallow decision tree classifier classify the data set based on just these 2 features. And the idea is that if a decision tree can classify it as well. This means there's like a good separation between the different regions, and say a decision tree of depth 4 or 5 is a relatively good proxy to what we can see with our eyes. So this means like there's like big rectangles for each of these classes. Here, by default, we show the 4 pairs that are most informative. So the 4 pairs where a decision tree applied just to these 2 features gives the best cross-validated accuracy. And we found this works pretty well across data sets. We do the same for principal components. So here you can see, for example, that looking at principal component 0 and principal component 4 gives the best overall, or is the most interesting according to our criterion, because it allows the best separation in this 2D space. And we also have the scree plot, which shows the explained variance of the different components. And lastly, we also show a linear discriminant analysis plot. So this is actually this is a supervised dimensionality reduction technique, or you can it's also a multi-class classifier, and in particular for somewhat low-dimensional data sets, this is really quite useful because sometimes it finds very interesting projections. And so here, each dimension, similar to PCA, is a linear combination of the input features. Only these are found to in a way that discriminates the best between classes. So what we can see here in this data set, something that wouldn't be obvious in the original data at all, is that there's a linear space, or there's like 2 linear components that if I project into these 2, then I can basically separate nearly all of the classes. Basically all of the classes except for the purple and red are separated in this 2D space. And so this is actually a technique that is not used that commonly, but I think it should be used much more frequently. You could also do more advanced manifold learning techniques. I found that they don't often provide very good results, so they're not used by default. Also, they might have longer run times. So next, you usually want to do some simple prototyping. And there's basically a list of models that usually are pretty instantaneous, that are hard-coded to Dabble, and basically they're always tried and implemented in a simple classifier. And the idea is that here they're basically instantaneous, and there's no point in not running them. And these are the dummy models, naive Bayes, decision sums, and some linear models. And these are basically always run, and cross-validation performance is shown. And here this is done in your adult data set, and while this is working, it gives you always the best results. So the dummy model is just a model that basically predicts the most common class, and this is useful as a benchmark or as a baseline. So you can see what the average precision or the accuracy would be if you do constant predictions. And then so Gaussian naive Bayes is a very quick classifier. And so basically they're ranked by how long they take. And so the first couple of ones are basically instantaneous, and then logistic regression might take a little bit of time, but not too much. But after running this, you will already have a reasonable baseline, and you could then go to model interpretation, for example. If you want to have more complex models, there's automatic model search, as I mentioned earlier. And so what this does is it searches over more linear models, random forest gradient boosting, and some cardinal methods. So this is sort of the slightly more complex models. There's currently no neural networks in there, mostly because I don't want to have a dependency on a deep learning library, though I might change my mind on that in the future. So the way it selects these more complex models is by using successive halving, which is basically a more efficient way to do grid search. So the idea in successive halving is to start with a small subset of your trained data set and evaluate all of the candidate models. So let's say all the points in your grid, and then throw away the worst half and keep the best half. And then the better half, for this you double the budget, so you double the training set size, and again you throw away the worst half and you retain the rest, and then you double your training set size again, and you run again. And so you always only keep the configurations or the grid points that perform that are in a better half for each of the training set sizes, and at each step you increase or double the training set size until you use the full data set. And so this can be shown that this actually is a very efficient way to search hyperparameters. More generally, this is known as multi-fidelity search. There's a particular variant called hyperbund that's very popular, but actually the successive halving, which is a simple variant, often works quite well. And so we are using this instead of doing a randomized search or grid search or something like this. And then what we're doing is not actually doing a grid search, but we work on a fixed portfolio. So we built a list of models that work well. And this list of models is not hard-coded, it's learned from a set of benchmark data sets. We're using the OpenML CC18, which is a list of, I think, 82 data sets. They're all classification data sets. They were curated as benchmarks for classification. And so for each of them, of these benchmark data sets, we run hyperparameter optimization, and then we get a list of good candidate models, and then basically we create a portfolio by doing a greedy search procedure among these. Though it's not entirely greedy, so we're not taking, say, the K best performing models, but we're using the models that, if you select the best one among these K models, you get the best performance. So this is basically trying to find a portfolio that is both diverse and performs well. And you can see more details on this in the paper Practical Automatic Machine Learning for the AutoML Challenge by Feuer et al. Here's some plots, not from their paper, but from a paper I worked on with some colleagues on multiple defaults, which goes actually in a little bit more detail on how to build these portfolios. In that paper, we did this for separate classifiers in scikit-learn for elastic net decision tree gradient boosting and so on. And for each of these, we built a portfolio with so here, number of evaluations is the size of the portfolio. So we did 1, 2, 5, 4, 8, 16, 32. And we compare that against doing model-based Bayesian optimization or randomized search. And if you have, if you look at very few candidates, using this portfolio works much, much better than doing random search, which is sort of expected, but also shows us we can get pretty good results even using a very small number of candidates. So in this paper, we didn't do this successive halving. We just evaluated all of them. In Dabble, I also do the successive halving on top of having this, this portfolio. And finally, Dabble has tools for model explanation. And so once you build your model, so this portfolio is implemented in any classifier. So there's two models. There's the simple classifier and the any classifier. The simple classifier is all the instantaneous ones. The any classifier is basically doing this successive halving on the portfolio. Then you can call explain, and explain will first give you metrics. So this is all the standard metrics you might expect. So this is shown here, the classification report from scikit-learn, which gives you precision recall F1 score, and then all the averages, your confusion matrix, and then ROC curves and precision recall curves. So this is basically all the things that you usually want to see. And then it also gives you model explanations. So if it's a linear model, it shows you coefficients or the most important coefficients. For tree-based model, it gives you the impurity-based feature importances, and then also permutation-based feature importances. So the permutation-based feature importances are often more robust because they computed on the test set, whereas the impurity-based importances are computed on the training set. And then finally, it also gives you partial dependence plots. So future goals for the library are to create more time-sensitive and faster portfolios, potentially also to allow giving a time budget, and to do model compression and building more explainable models on top of the more complex models, and to improve the model inspection. So right now, the model inspection is like a little bit bare bones, but it's getting there. So if you want to try this, you can just do pip install Dabble. You can check out the website and for documentation and tutorials. And if you try it out, you have any issues, please contact me. I'm really happy to get any feedback. And so you can find me on various social media or send me an email or go to the Dabble issue tracker. All right, thank you so much for your attention.